Okay, welcome. Let's get started. I hope you had a great weekend. Again, I'm thrilled that you're here on such a beautiful spring day. It is just amazing outside. It's wonderful weather. If you go out and it's raining blossoms, you know things are fantastic. So today we're going to talk about population projection, stable age structure. Announcements are, my apologies for not making this clearer earlier. There will be nothing to turn in for Lab 5. So there effectively is no Lab 5. You still get your 2 free labs out of the remaining 10 labs that will be graded on a check plus, check minus basis. So there's nothing to turn in for Lab 5. There is, as we will see, a part where you are asked to reflect for self-study or self-reflection. So you are on your own recognizance to do that, if that's the right word. Your word of honor to do your self-reflection of the lab. There's nothing to turn in. Next Monday, we will distribute the spring 2019 midterm without answers. There is an answer key, but we will be available to discuss the answers, and in particular, a week from, not this Thursday, but a week from Thursday, so next Thursday, an in-class review, and then 2 weeks from today is the in-class midterm exam. 1 week from today is Super Tuesday, too. So if you haven't voted yet, and I haven't, I have a mail-in vote. You might want to think about doing that. It is ridiculous how quickly we are hurtling toward big decision points these days. Questions about the class logistics? So remember to vote on Super Tuesday if you're registered to vote in California, or I think Texas also votes the same day. A bunch of places vote. It's going to be a very interesting Wednesday, I guess, that week. Okay. So why do we care about age structure? I wish I had led off with current events, I think, are a little bit more compelling. This is still pretty compelling. So you should be concerned about Social Security, and not in the sense of sort of a doom view of how it's not going to be there for you, because that could be true to some extent, but I think it is almost a total certainty that the taxes on your earnings will be there for you, even if the Social Security benefits may not be there for you in the same amount that they have been there for my parents and for your parents probably, and your grandparents and your grandparents' parents and all of those generations of Americans. In the United States in 2020, the age structure matters a lot. And so right now we're looking at a situation of about 28 retirees for every 100 working age people. And we're doing sort of broad brush here. If you're like me, you know a lot of people who are over age 65 who actually are not retired. This is a broad brush, back of the envelope kind of thing. It's true that retirement doesn't always happen at age 65. And even, sometimes people retire and then they come back out of retirement and all that. So I wouldn't say this is antiquated. If you look around the world, 65 still is a pretty typical age of retirement, and so it's still a pretty useful metric for what I'm going to show you on the next slide. In 2040, which once seemed like a long ways away, I think the forecast, and we'll talk about this more next time, but I think the forecast is for the Social Security Trust Fund to be exhausted by 2040. Sometime I think it probably is going to happen in the late 2030s. It's only 20 years from now. You will be of prime working age. I will be in the twilight of my working. I hope I'll be 66 in 20 years. Man, it's insane. And at that point, I will be roughly just about to join the ranks of retirees, or technically by this measure, I will be among the 38 retirees per 100 workers. And so this is an increase of about a third. So it's roughly going from 30 up to 40, which is an increase of about a third, and that's a pretty big deal. And so that means that, and again, we'll return to this next time, to sustain Social Security, the tax rate on your earnings would have to rise by about a third, which is a pretty big hit. If, we keep the same benefit payout, and of course, I think a system that needs to adjust is going to adjust along several dimensions. And one of them is probably a higher tax rate on you guys and maybe on me. And part of it also is probably a lower benefit rate paid out to me and maybe your parents. We'll have to see. But my parents and Emeritus Professor Ronald Lee and other people of that age who are approaching late 70s and 80s, they've already gotten their Social Security. Donald Trump and Bernie Sanders and all of those old people like Elizabeth Warren, they've already gotten their benefits and they look like they're going to get them. So one thing you might keep in mind as Super Tuesday approaches is you might vote for somebody who's thinking about how to fix this issue rather than talking about immigration or something. This seems a little bit less relevant. So here's the thing, though. Things could be a lot worse. Here's the United States. Things are better right now in China, but look at what is going to happen in China over the next 40 years. So in 2040, a ratio here of about 20% doubles and then triples. I mean, look at that. And of course, what does that reflect in China? Why is this happening? I'll start you off. The one-child policy. Yeah. So that recently was, I guess, the big question of, well, is that still in effect in China or not? And I think it was formally repealed, whatever that means exactly. But this is a big problem that is looming. And here's the remarkable thing. So looking at 2060, so we're starting off older in this metric than China, and we're ending up younger than China in this metric. And part of it is the one-child policy. Another big part of it, though, also is immigration. So China, I think, probably has net out migration. I think I don't know, but we have net in migration, and it makes us younger, and thus this is lower than it otherwise would be because of immigration. Japan is already just a total mess with the age structure in this regard. Now, it's not. I don't mean to say that Japan is a total mess. I'm just saying that Japan is an old society already, and it's going to get even older. Immigration into Japan is very, very, very minimal. And fertility is really low, and this is scary to me. 83 retirees per worker in 2060. Yeah, I don't know how that's all going to work out. So this is why age structure is important. So we're going to talk about this. There's a lot of numbers and fun theory and things like that, and I just thought this was so funny. This is actually not technically my father's riddle. It's Professor Josh Goldstein's father's riddle. So it's in there, and it's a useful didactic mechanism of thinking about, well, what makes a country young or old? And I told you a couple of things. One is low fertility, and another is no immigration. Well, if you have low fertility, does a country just keep getting older and older and older, or the reverse? How does that all work? And it turns out it's a little more complicated with some very nifty math that Professor Goldstein also has donated to us, and we'll look at. So we'll look at the app. We'll look at the lab. So Lab 5 is in class. We'll step through it today. And I think, too, this might be review for some of you, and it might be brand new for some of you, and it might be very confusing. So we'll try to make this a little bit clearer in our step-throughs, and then we'll do some of this, some nifty looking at pictures and some fun, it's really fun symbolic math. So if you like the math, there's plenty of it for sure. So I wrote this slide yesterday, and let me quickly run through it because, of course, this is no longer current. These days, if we're tracking the coronavirus, as soon as you write the slide, it's already out of date. And so there's brand new developments that I also want to show you that are not in the slides. Current events then, so maybe, and this is way out of date. So I think the number of deaths worldwide is probably more like 3,000. And the big development 1 or 2 days ago was Italy reporting 6 deaths in the north around Milan, which has a big airport. One of the questions is, well, how is the coronavirus showing up in places? And it has to be people transmitting it. And it could be travelers by aircraft, or it could be shipments of goods with people moving the goods and then transmitting the thing and all that. And then the thing that's not in the slide here, so I think maybe it hit the news this morning, but so Iran is also hard hit by the coronavirus, it appears, and they trade a lot with China. And the most just sad irony you've ever seen was like a health minister in Iran, I think on Sunday, proclaiming that Iran was totally coronavirus-free and coughing and sweating while he did that, saying that, oh, we don't have coronavirus, and now he has coronavirus, confirmed. So, and there's irony there that makes us laugh, but, the sad thing is that, we will see how this plays out in our country with the government and news and keeping the public informed in a way that is useful. Places like Iran really struggle with that, as many of you may well know much better than I do. So it's wry commentary on the state of the government in Iran, where there's an issue of, well, when do you know certain things? But there's also a lot of propaganda that gets told. And so you might wonder, though, well, if you're talking about a contagion, where is the line that, between, sort of positive propaganda and, so you might sort of be, well, optimistic about things and happy and all that. And then kind of the other extreme is you might say that people are dying, and that might create a lot of pandemonium. So where in the middle are you going to be? And, well, we'll talk about that more. I wanted to mention this, though. So I had a good time tweeting this out, this article that people seem to like on that silly website called Twitter, an article all about the male-female differences in the impacts of coronavirus. And I think the knowledge we have mostly comes out of China, which is hardest hit, and so has the most cases. And it turns out that it was fascinating to me. There are biological reasons and then behavioral reasons why women are less at risk of bad outcomes, and I think also less at risk of actually contracting the disease to begin with, as we'll get to in a second. So estrogen, it turns out, is the reproductive hormone that women have and men do not have. Testosterone is the one that men have. And it turns out that at least with SARS, scientists were able to actually turn on and off the estrogen and the testosterone in mice, which biologically are quite similar genetically to humans. And it turns out that estrogen in the X chromosome appears to actually affect immunity, and the Y chromosome and testosterone does not. So biologically, there actually is a reason why women might have more immunity than men do. But just the fascinating thing to me, as I'm a social scientist, I'm not a biologist, is this whole thing about the behavioral side. So smoking, I think maybe we mentioned this last time. So and the article mentions this, more than half of Chinese men smoke cigarettes, and about 2% of Chinese women smoke cigarettes. And the thing about smoking is, admittedly, if you stop smoking, your lungs can recover, but as long as you're doing it, your lungs are taking a pretty bad hit. And if you have weakened lungs, that's where the pneumonia is going to catch and kill you from something like coronavirus. So there's that, there's the smoking, and then this was just astonishing to me. And so I don't know the study this refers to, but the article says that hand washing is lacking among males. So it's less common, even when people are sort of told to wash their hands, even healthcare workers. So male versus female healthcare workers. Apparently somebody had studied this and found that females are better at actually washing their hands than males are. So everybody wash your hands, especially the men in the room, please. So now let me pop out and show you the most latest development, and it speaks to this issue of what, say, Iran and China are struggling with. So here is, I like going to NPR because I think generally it takes the most sort of sober, it's a catchy headline, but it's reporting that's fairly, just the facts, not crazy. And so this just happened, I think, so about 11:30 our time, health officials, and that means the Center for Disease Control, the CDC, actually have said this. So start planning for the spread of coronavirus in the United States. And, these are pretty tasty quotes. So here is, I don't know her, but Dr. Nancy Messonnier of the CDC saying it's not so much a question of if this will happen anymore, but really a question of when it will happen and how many people in the country will have severe illness. And she talks about, thinking about preparation. And I think, we should all take this to heart. It's nothing to get overly concerned about, but, there is this disease that, it's like the flu, and we have a flu shot for the seasonal flu, but we don't have any vaccination developed yet for this. It's also like, seasonal colds. And, it was just colds that landed, my 1-year-old in the hospital. Colds are bad, and so is this. So it's not like it's cataclysmic, but, it's important to think about this. So, and then she relates how, she had a conversation with family over breakfast this morning, and just thinking about, school closings, workplace shutdowns, and the possibility of these sorts of things. How do we prepare for that? And the answer is, well, just think about it. It might happen, and what would you do if it did? Would you hop in your car and drive home? Would you go take a vacation? Would you just play a bunch of video games in your dorm room? Or I don't know, whatever you might do. Would you telecommute? It's useful to think about that. So that's one side of things. I wonder if CNN and Fox might be a useful one to look at here too. I don't know what they are saying. So that's the top news here, but of course the other side of things, the president is in India right now and was quoted as basically saying the reverse, which is everything's great. I think things are great. Fine. It's going to go away. And so maybe Fox has that. I don't know. Let's see. And so how this plays out is going to be interesting. Okay, right. Obviously, so the top headline on Fox News is something about Trump, Ted Cruz, and one of the Supreme Court justices. Who cares, honestly? Who cares? So they're not even covering it. Not surprising. That's kind of the way that goes. Yeah. Oh, it's on the bottom, way down here? Alert. Along the bottom, alert the world. Okay, so that's a quote from the WHO. Heaven forbid. Okay, all right, so here's the tiny, tiny little headline right there on Fox News saying that the CDC, and so it's going to be interesting to see whether this CDC official retains their job, because that's the way it's been going recently in this administration, and I hope that person is kept. It's Messonnier again, it looks like.
At least 6
So I
people
mean, the
have
latest,
died from the
prior to
virus
this, it
in
was this
Italy,
ridiculous
with more
thing
than
about the hurricane and the National Weather Service that Trump and the Sharpie. It's the dumbest thing. Just Google Hurricane Sharpie Trump, and you'll find this ridiculous story. And that's this kind of thing that developing countries struggle with is, well, what do the politicians say because what's in their best interest, or what do they even know? And that's why you have an executive branch filled with people at the CDC who actually know what they're talking about, and you rely on them rather than just making stuff up. So that's obviously important. Okay. So, well, that's all I've got to say about current events and the coronavirus and all that. Now I've got to move on and dazzle you with population aging and age structure. Any questions about this? Remarks? So big gatherings of people are potentially a risk. We will see. I mean, UC Berkeley really stays on top of this stuff. So if things look a little interesting, we'll let you know. If you're not feeling well, stay home. It's a great option to do. We record the classes. You can always watch the video and interact online. Use your own best judgment at this point. Okay, so much more exciting. Population age pyramids. So this is, these are age pyramids here from the United Nations projecting the whole world population in 1950, roughly where we are now in 2010. I'll read, of course, a little out of date. 2050 and 2100. So this is, in 2050, kind of the classic pyramid shape, right? It kind of looks like a triangle. Here, fairly triangular. I don't know what that is. It sort of looks like half of a football. And here it definitely looks a little bit non-pyramidal, right? It's, population age pyramids look like pyramids in certain contexts. So when you have fairly high fertility and fairly high mortality, which was generally true up to about 1950 when things really started to change. So big reductions in fertility, but also big improvements in mortality here at these older ages. And what we are seeing then is the playing out of a big fertility decline. So we saw that in the slides on global warming, the Nordhaus material and all that. We saw the big forecast of the reduction in the total fertility rate. And it's also reductions in mortality, which is, of course, a very good thing, the changing shape of the survivorship schedule, which we'll look at shortly. Here's poor Japan. I don't mean to rag on Japan. Japan's a fantastic place. I highly recommend visiting and enjoying everything. Japan is struggling with its demography. So here's Japan in 2000, and if you squint, so people living in 2000, if they were age 60, that meant they were born in 1940. So you see a great big notch eaten out here of this is the female side, and I think also probably a notch over here if I can line that up in my squinting. I'm getting farsighted. I can't even see this. I'm getting old. 20 years, I'll be a retiree, and you'll be paying my Social Security, whatever there is of it. All right, so here's age 60, and so there's some reduction in males there as well. With population age pyramids, you'll see these notches here. This is an interesting one. I remember trying to think about this. So here's 2000, this is got to be 1960, right? That's about age 40, is that right? Man, I should have brought my reading glasses. Age 35 or 40. You'll see these notches, especially I think it's true in the case of, say, China in an age pyramid. There are certain years in which and I'm going to totally massacre what this is, but it's sort of the Chinese zodiac, I want to say. It's like the year of the dragon or the year of the whatever, and some of them are unlucky. And you'll actually see that show up in the population totals because it was considered unlucky to have a child born during that year. So that's part of what you might see as fertility choice, where you slam on the brakes and you don't have your child because it's thought to be an unlucky year in some societies. The other big story then would usually be warfare. Not always, could be like a natural disaster or something if it really had some ridiculous toll on population. Here then, on the right-hand side, 2050, we don't, this is a forecast, so there isn't really anything in terms of a jagged anything, thankfully, right? Because, warfare is, of course, very bad. You still see a little bit of a chunk here, so this is the 85-year-olds aged another 50 years, so it must be this thing moved along in time. So it must be 35, I guess, if I get that right. So 50 years later, they're up here. And so there's a reduction in folks at 35. There must have been something in 1965, I guess, right, in Japan. Okay, so let's go ahead and run an iClicker. And here, I understand that I haven't really formalized a lot of this, but let's talk about age pyramids. Population age pyramids, which one's true? A, they always look like pyramids. B, they never look like pyramids. C, they're broad at the bottom when the population is relatively young, broad at the top. Answer D, when population is relatively young. Or E, none of these. Okay, and so let's close polling. 3, 2, 1. Polling closed. So I think the best answer here would be C. They're broad at the bottom when the population is relatively young. Good job. Broad at the top when relatively young. Yeah, not so much. Yeah, none of these. I guess E is probably the second best, but answer C is right. So they're broad at the bottom when the population is relatively young, and that's almost just tautologically true. So just backing up, I guess that's probably worth doing. The population age pyramid, maybe it's easier to see right here. It's the younger ages at the bottom, so if it's broader there, you've got more young people. Yeah. Okay, how about another one? Why might a population age pyramid not be symmetrical side to side? So in other words, there's a top and bottom, right? And there's broad at the bottom means it's young, but there's also a side to side. There's males, I guess, typically on the left, and on the right are females. Which one of these would be a reason why this is the case? Why might a population age pyramid not be symmetrical side to side? And please do feel free to discuss with your neighbors and friends. Okay, so this is a little harder, so let's close polling. In 3, 2, 1, let's close polling. Okay, so I think here the best answer is E, that past warfare has tended to kill males more. It's not exclusively true. I think if you look at a Russian age pyramid, you probably would see a decent amount of female casualties as well. But usually it's the males who have traditionally been the combatants in warfare. Usually you'll see the males existing not as much anymore, so I think E is probably the best answer. Okay, good. And so the other ones, I think I tried to trick you by listing things that mostly were true. A is rather clearly false, that males and females are not the same. They are, I guess, the same in some ways, but in many ways they're not the same. B, mortality rates rise strongly with age, is true, but it doesn't help us understand this point. The mortality rates rising a lot with age explains why an age pyramid might be rather tapering up at the top, right? Because people are dying and they're not reaching much further than the very tippity top sort of maximum age that people maybe might be able to live to, something like that. C, fertility rates fall with development is also a true statement, but does it help us understand the back and forth? Gosh, did anybody say that? Because I just am thinking of something. So some people said C. I think there might be one way in which this could be somewhat true. So if fertility rates fall a ton, let's suppose they fall all the way down to like 1 child per woman. And then the question is, well, what sort of child do you want? And you might, the traditional choices there are, well, highly educated, right? We're all here in this room, and so we know that parents typically choose that. But what else do parents choose for their kids? Well, the science allows you to do some sex selection, and also other more blunt things allow you to do that as well. And so there is a way in which this might matter, actually, for the side-to-side, males to female ratio. To what extent might you find, gender preferences in children? And there's a big literature that looks at this question. It's usually phrased in terms of missing females. Not in all societies, but that can happen. So that's something that's true, kind of a big bummer. Okay, so moving on from the big bummer, the D, vital rates are always changing, not stable, is also true. And does it help us understand the symmetrical from side to side? I don't think so, because although the vital rates change a lot, they don't usually do that in some systematic way with regard to the incidence on sex, whether it's fertility rates or mortality rates for little boys or little girls or old people or all that sort of thing. Okay, so good job. The best answer there is probably E. Questions? All right. So Josh Goldstein's father's riddle. Not my dad. I don't think he's ever said anything like this. My dad does speak in riddles like a lot of fathers do, but I don't think he said this one. Yeah, one thing he does, and your parents may do this too, is they speak in what are called idioms, and he's inherited a lot of the idioms from his father. Idiomatic language means that what you say is sort of a metaphor for something else, and it can be so distantly related that especially non-native speakers would just never understand what in the world that meant. And one of the ones I can remember was that growing up in Missouri, apparently my father's father would say, well, if things are going well for you, he would say, you're walking in tall cotton. I was like, what in the world does that mean? And I think if you're picking cotton and it's tall, well, you get to pick it up here instead of down here. I think that's the only thing that means. But I couldn't tell you for sure, and most people with the idioms probably couldn't tell you. Okay, so the riddle is, if a population has very low fertility, won't it just keep getting older and older and older? That's kind of a really good question in light of what we saw back here, right? Is this going to happen forever? And boy, looking at the statistics, of course, what's forever? That's kind of maybe the question that gets raised by this, because here's Japan, getting older and older and older. And the sad truth is then, this part here, vital rates are always changing, not stable, kind of is part of the challenge with Japan. It turns out that mortality rates kind of just keep falling, which is a very good thing. So, but the riddle is, well, suppose you have very low fertility, won't Japan say just keep getting older and older and older? Well, there's a way of working this out with the math, and the answer is going to be no, actually, that there's a stable age structure that pops out of things, but it does require there to be no change in the fertility or mortality rates. And so that's what, the tough thing. It's like, well, we're setting out, population has very low fertility. In other words, the level of fertility is very, very low. It's not a statement about it getting even lower, which in Japan I'm not sure it could. But it turns out behind the scenes, mortality is getting lower and lower and lower and lower. And it's even doing that here as well. So this is a slide for the United States. If we saw this for Japan, it would be rising, I think, even more robustly, at least in the recent period. Period life expectancy at birth, and it is a number like 78 or 79, and it is an average length of life. So if this number, if this statistic equals 79, that's an average length of human life that is equal to 79 years. What else is shown here? So in addition to time, so we've got this series from, it's coming out of the Human Mortality Database, which is headquartered right up here and also is a joint thing with Max Planck over in Germany, but it's headquartered up here in UC Berkeley. It's awesome. And they're great people who work on this, and they produce these statistics. So all the way back to 1933, I think is where the series starts, and there's a little bit, jumps and hiccups and all that, and then a pretty remarkable rise with a few plateaus in between. And what else pops out here? Well, the female life expectancy at birth during this period was always greater than the male life expectancy at birth. And so here are the males down here in red. So this may be broadly known, but this is true that the females have lower mortality rates at every age in advanced societies. So that can be different if you're thinking about either historical periods or also developing countries. But women live longer, they have lower mortality rates, and it's awesome. What has been not so awesome recently is this. So first reported so this is now 4 years ago, isn't it? And it was in December 2016, so it was after the election. The data for 2015 were first reported. And this really did happen. Now, I think there's some question in my mind about whether this was the first time this ever did happen. And I think actually this is not, it had happened before. The life expectancy actually fell. So it's a forecast of an average length of life, and I'll talk more about that in a second. But it's in some sense a forecast based on current data, and it actually fell, and it edged down. It's not a huge reduction. It means it's only about 0.15 year different, right? It's between 78.91 and 79.06. But it did fall, and I think, so these data which end in 2017 do not show an increase. I think the most recent data out of CDC does show a small increase again. And why? What was this pinned on? Does anybody remember? Why would length of life decrease? Mortality rises, right? I mean, that's tautologically true, but the underlying sort of mechanisms here, like why would the length of life fall? Well, you could get into more car accidents, you could die of more cancer or more heart disease, or what? Drugs, right? Opioids, it's drugs. It's ODs, and it's associated diseases. So if you're high, you can also kill somebody or commit suicide. That's the other thing. So there's some component of those causes of death that are associated with this. So what is period life expectancy? Well, first of all, it's the only thing you're ever going to hear in the news or on Twitter or on your social media. And it might be the only thing that you ever will hear about from insurance companies, even though they actually should know better. It's the average years of life lived if somebody faced the mortality rates prevailing in a given year over that person's entire life. So it's fictional. There's no way to do this. What you do is you measure the mortality rates for all age groups in a particular year. So the deaths in a year, and then you look at the mid-year population, and you're figuring out death rates that way. And that gives you the period life expectancy of some fictional strange unicorn of a person who is born and dies in the same year, subject to all those rates. Cohort life expectancy is the number that we actually care about. It's what, say, in my birth cohort of the early 1970s, my colleagues and I are all subject to. The age-specific, period-specific mortality rates starting in the early 1970s, and then the mortality in the 1980s, and the 90s, all in prehistory, right? And then finally 2000s, and you guys are around, and then 2010s and 2020s. And so the cohort measure is the thing that kind of, takes a little bit of mortality in each of these historical periods and also into the future. And of course, the big problem is that we don't know the mortality rates that I will face next year and 10 years from now, 20 years from now, and we definitely don't know what you will face in the future. So period mortality measures are very useful. They provide some kind of sense about where we might be headed because we don't know yet. And there's more to say, obviously. So take Demography 110 to find out more about this. Some useful tips is that if mortality is falling, cohort life expectancy will be longer than period life expectancy. And so stepping back in the previous slide, so this is an underestimate for all of you for at least two reasons. One is the reason I just said, that mortality rates are still falling. That's one reason. The other reason is that this is actually period life expectancy at birth, and you have already weathered the storms of 20 years of mortality risk. So your length of life conditional living to age 20 is higher than it was at birth because you made it through 20 years of not dying. And so that's another reason it'll be higher. So period life expectancy is what we can measure now, and it's useful. And if you want to know more, take Demography 110. There's a lot of interesting science to be said about this. Jobs and insurance and finance in general. There are a lot of financial products that are associated with length of life and mortality, whether it's life insurance or annuities. Annuities are products that pay people a certain amount of money if they are alive. And so that, is sort of the reverse then. Life insurance gets paid out if you die. Annuities get paid out as long as you are living. So how does this all happen? You calculate age-specific mortality rates, convert to death probabilities. This is sort of all true but not really relevant to class material. It's sort of too detailed. And what you do is you chain together the death probabilities to find the ski slope, which I'll show you in a second, the schedule of what's called survivorship at age X. And I have never been able to figure out why we call it script L or cursive lowercase l, but we do. And I don't know why, but we do in demography. We call it that. You could call it something different if you like. You could call it little s for survivorship or something. And then life expectancy at age X is the sum from X to infinity of the area under the survivorship curve. It's, if you like, the probability of being alive times this little amount of age. The dA is kind of the point here of the x-axis, right? How much of this length of life that you actually live times the probability of being alive. And so as the probability changes, and it looks like this, so you start off quite high. This is for both sexes combined. It's almost imperceptible, but there is a reduction here, and that's the horrible tragedy of infant mortality just after birth. So you have to be a live birth to get measured here, but then you might die immediately, and that shows up here. So the first 20 years are usually not that eventful. So when I told you it's conditional on you getting through 20 years of life, that's true, but you probably in your head said, well, that was easy. And it is, but for some groups it's a little bit less easy. And here's the ski slope of survivorship, and we're doing pretty well. This is sort of the bunny slope up here at the top. And all of a sudden, black diamond, and here's off we go into death. It's rather likely at this point. So that's the survivorship curve, LX. Here's life expectancy at birth, and you notice, and it's because of the skewness here, if you thought about the probabilities that are underneath this, the additive. This is the cumulative density function, and that's the CDF, and you thought about the probability density function was the PDF, what that looks like. That starts at 0, and so it's the probability of dying at a particular age, and it goes like this, and it's very skewed. And so the mean here, the average is 78.86, but the median, of course, is actually given by this guy, 50% dead at age, whatever that is, like 85 or something like that. And there are other things that matter as well. Okay, so why am I showing you this, all this fun mathy demography? Well, it's true. Now notice what happens in your head. So think about if I were to take this picture and just twist it counterclockwise by 90 degrees, I get that. And then suppose I just sort of flipped it, made a copy flipped right through the axes there. And so what does that look like? Kind of like a pyramid. Maybe a little bit more like half of an hourglass, right? It's sort of, a little tiny neck up there of those wonderful people who are left way up there at the top, and then this big, widening here. And of course, we're in a situation where, thankfully, most of the mortality is up in these ages. So these are pretty advanced ages, 70, 80, 90 up here. I just want to take this moment to boast that my paternal grandmother is turning 100, and that is awesome. She's not one of a kind, yeah, but that's a very low probability event, and she's cool. Okay, so survivorship does this for you. This is the shape that pops out if you did this, and then we'll talk about, well, why might you want to do that? After we look at some really just thrilling stuff, right? Matrix notation is just thrilling, isn't it? Okay. So, oh, how many people just detested linear algebra, right? Really? Okay, how many people took linear algebra? Okay. Of those of you who took linear algebra, who detested it? I don't know. I just detested it. I couldn't stand it. Linear algebra. But, you know, underneath it all, the tools here of linear algebra, it turns out, are very helpful. So this is linear algebra. It's matrices and vectors and all this stuff. I think the extra jump, say again, oh, the what? Mic's turned off. All right, matrix notation and rules about stuff. So why are we doing all this? It turns out it's a parsimonious and powerful way of trying to represent things that we care about, which is evolution of things like population over time. And ultimately, if you didn't detest linear algebra, my hat is off to you. I hated it. I couldn't stand it at all. But it turns out that underneath a lot of that, then spawns stuff like econometrics and statistical analyses that are very, very useful. Lucky thing is, you don't need to really know a lot of this usually for doing econometrics and statistics. What is this going to look like? So suppose we've got some starting population vector P0. Then applying some kind of matrix to it here, and it gets, so it's left multiplied, I think was the way this is usually described. Then what you're going to end up with then is another vector the same size as P. So you need to have the thing kind of on the correct side to multiply and get the right thing that you want. And so in general, this is what we might see, and we're going to use a 3x3 matrix. So here's our matrix A with the little a's then are the units that are actually, or elements I should say, that are actually in here. And so I think, so we've got, here's row 1, here's row 2, row 3. So A1, 2 is the first row, second column item, and then there's a third row, third column, and all that. And so here then is our population vector. So there's a P1 at time t, a P2 at time t, and a P3 at time t. And those are going to be our different age categories of people. So a population vector with different age groups in here. And then the product of these two things is going to then be a new population vector at time t plus 1, where I probably should have written it differently too. One of the confusing things is to remember that if these are age groups, then we're going to require t to be indexed basically in the units of these ages. So if there are 20 years of age in each of these groups, then each of the time steps needs to be 20 years of time. And so that's an unfortunate gotcha there. Okay, so now writing out what this might look like, the vector, matrix vector product looks like this, if I did it right. Right? So here's A11 times the first element of this. So that's in the first row here. The next piece then is plus the second element here times the second element going down the vector over here, plus A13 times this element here on the bottom. So these guys in the top row are all multiplying each one of these, and they're giving us the new top row. So that's important because when this is the population age structure vector, the top row has to be the youngest group. And then the next one down is the next youngest. But the youngest group, of course, is very special. Provided that you don't have immigration, these are the babies. They're the only new entrants into the population that you can have. So they have to show up here in these elements that are along the top row of this matrix. Okay. So here are the elements A21, 22, and A23. I hope I wrote those all out right, and they're multiplying these guys, and then here are the bottom elements. So one of the things in the lab is, the question is, well, can you think about if we're in the population setting where what we're doing is we're mapping how these population age totals change into the next period's age totals, are any of these things, do any of them need to be 0? And the answer usually is because people don't age backwards, even though that might be nice. I wouldn't mind that. But you can't go from being in group 2 back to being in group 1. So group 2 is going to be ages 20 to 39, And so the only way for you to go is either out through death or to the next group, the next older group, which is ages 40 through 59. And then, of course, they fall off a cliff and don't exist anymore. So some of these, then, in the population setting are going to be zeros. And I think if I can eyeball it, it's this one. It's the group that ends up jumping. This would be the leapfrog group, right? So we don't have anybody going from the youngest age group all the way to the bottom row here. They have to go into the middle row first. So this one's 0. This is going to be some number that represents the number of P2s that survive into P3. And this is the bottom row. And then this number here, A33, would have been the number of P3s who just stick around and don't age. That is also 0, right? Nobody just sticks around and doesn't age. Everybody has to age. So this is going to be 0. That's going to be 0. And a similar story up here. But the logic is that I think it's A22 is 0 and A23 is 0. But this one is some number. It represents the P1s, these folks who live into the next row, who actually survive. So confusing, ultimately, it's a useful way of drawing all this, and it reveals some pretty cool things because we can get our studio to do all this pretty quickly. So next period's newborns are on the top of the row, and it's only the top row then that supplies the fertility rates that create the newborns. So the fertility rates are all these sorts of things, and everything else then would be reflecting survival or the lack, say, of backward aging or sticking around or something like that. Okay, so we're going to do the lab in a second, but before we do, I wanted to ask you a few other things just to make sure we're all staying current. Because period life expectancy is 81.4 for females and 76.3 for males, which one of these is true? And do please discuss with your neighbors and friends. Okay, so let's close polling. 3, 2, 1. Okay, so I think the best answer here is A, that females enjoy longer lifespans than males. The next one you might guess, I mean, E is funny, but it's not true, right? I mean, I would be willing to take anybody's money on this. There's absolutely no way that we are all going to die before reaching age 70. Absolutely no way in the world. Never going to happen. A female baby born today will live 81.4 years. It's probably the closest to true here, but it's not true. It would only be the case if that female baby actually somehow magically lived her entire life in this 1 year. And so, yeah, A is the best answer. D is kind of second best, but again, it's not quite right because it's the period life expectancy today is 81.4. And the thing is that a female baby born today will live let's say 80 years into the future, which gets us to the year, my goodness, 2100. Isn't that amazing, right? I was just mind blown because my younger daughter is going to live until the year 2100 when hopefully the oceans haven't swallowed us all. The other ones are probably not the best answers that, male students and female students, it's the same kind of story. Definitely not true that, so it's not the right statistic for me, and it's because of the issue of conditional probability. So I've already lived to age 46, so even if that were the right number for me, which it isn't, it gets a little fuzzy because then you might wonder, well, period and cohort. Anyway, that's, a discussion for another time. Okay, so moving right along. How about this one? I think the probability that I will still be alive at age 75 is what? So I've given you some guardrails here. I've not allowed anybody to say 0, and not allowed anybody to say 100 either. And so, and just as a side note for the propeller heads like me, this is actually the ratio of the cohort L's. So L75 or L20, which is a little bit hard to get one's head around. What do you think the probability is? And so some guardrails. How would you go about thinking about this? This is a tough one, right? You might think a little bit about your grandparents, perhaps, and how many of them were still around at this age. That might help. Yeah, question. Let's come back to that in a second. Okay, so let's close polling in 3, 2, 1. Okay, and so what do folks think? And so there's no right answer here. A good mix. So I'll have a look at these and see what the average is. I mean, so the mode is obviously it's C. It's 70%. Not bad. And so let me just ask a few more questions before showing you something that might be useful. Yeah, I mean, it's totally okay to be like, I have no idea. Right? I mean, that's reasonable. If I didn't, so my rule of thumb to you was, well, you might think about your grandparents, and you know, we've got 4 biological grandparents, and so you've got 4 different realizations. The problem is, of course, there's 2 males and 2 females in the biological grandparents. So that's a little hard to think about, but let's just treat them all the same. And so think about how many of them were alive at age 75, and I think mine were 2 and 0. So I think that gives me a 50% chance. But so if you had 3 alive at age 75, that's 70%. And of course, then the problem is that you are obviously not your grandparents. You have better survival than they did. And so I might bump mine up to 60 or 70 or something like that from 50. So that's one way of thinking about it. Okay. We measured this earlier, but just when we look at the data, I'd love to be able to do this. So if we could just have you tell me this again so I could get this straight when we look at what your answers were. And just as a side note, so please, again, if you wouldn't mind, please respond the way that you think is correct. The side note that's interesting here is you might ask yourself, well, so females should have answered a larger number on the previous slide, but did they? And the reason is females are answering for themselves, males are answering for themselves. Which of those 2 groups do you think is likely to overstate their survivorship probability? So let's close polling in 3, 2, 1, please. Okay, thank you very much. Okay, and so finally, let me ask this one. I'm also going to ask this next one too. I'll ask that too. So I'm going to ask vape or smoke e-cigarettes. So this one, just tell me if you currently smoke cigarettes, the traditional Marlboro Man or whatever. Right? That old weird geriatric thing, you know, the guy who's too suntanned even though he's wearing a hat. And you can say we don't know or refuse to answer. Okay, so why don't we close polling? Do you currently smoke? And so, you know, there are also ifs, ands, or buts about that. Please just answer in a way that you think is you know, you would tell somebody. Okay, and so let's close polling in 3, 2, 1. Okay, and so now let's look at the results. So 7%, and there are some who say, I don't know. That's a good answer. Well, maybe they've actually kind of tricked us, right? Because they don't, it's like, well, how, you know, suppose you live with somebody who smokes. How much do you smoke because of the secondhand smoke? So let's do this one now. Do you currently vape or smoke e-cigarettes? And so this was a really, you know, interesting frontier in health economics, is what connection there is between this behavior and the one on the previous slide and other things like prices and knowledge too, for that matter. Okay, so let's go ahead and close polling. And I'm really interested to see about this one. I'm also interested to see the crosstab that who, you know, the overlap of folks who say they smoke cigarettes and those who say they smoke e-cigarettes or vape. And so let's close polling here on 3, 2, 1. So what do you think? Is it going to be higher than 7%? Yeah, double. That's interesting. Again, the folks, the smarty pantses who say, I don't know. Okay, so thank you. That's going to be very interesting. I'll look at that and we'll talk about it next time. to double, well, and then you want to ask yourself this. So are the 15 percentage points, are those different people, or are the 7 percentage points of people who smoke cigarettes, are they subsumed in that? And I don't know, we'll have to look. One would expect that those are probably substitutes, that if you smoke cigarettes, you do not vape, and vice versa, maybe, but I don't really know. You might, and I don't know, yeah, but the substitute view is certainly the one that my friends seem to have shown me, is that you either do one or the other. And of course, the big thing in your head, and so you might very smartly say this to me, I'm pretty aware that there are health risks associated with cigarette smoking, but I'm not so sure about vaping and e-cigarettes, and I would agree with you. Now, the weird thing that has happened is, and I don't know what the state of this currently is, but the Trump administration wanted to restrict e-cigarettes, and it's because there was a bout of some very strange lung ailments and I think deaths among people who self-reported vaping. But one of the big problems, well, there are two big problems. One, the regulation of vaping products is not at all what the regulation of tobacco products is. And so there's a big question mark about what is actually in e-cigarettes. And the other problem is that you don't really know for sure what somebody who vapes is also doing. You could be doing other things when you're vaping, and meaning other sort of chemical stuff. And it's because you could lace a cigarette with stuff if you wanted to, but it's I think much easier, right, if you vape, to actually lace it with something else and have a good time. Okay, well, anyway, we'll talk more about that next time. So let's now do our RStudio lab. We'll give it a shot here. And so let me say a few things about the rules. So no migration. And so you've got a closed population. You've got births and deaths only. We're going to combine sexes if you like, or there is no sex. Everyone is female. Either way you want to think about it is fine. But the point is just that this is a complication when you do the mathematical modeling to have two sexes. And so usually what happens is you just simplify and say, okay, let's have one sex alone. We'll have age determining birth and death rates, and these age-specific birth and death rates are constant. And so that's pretty important to get the result. Okay, so let me also say, let's do this too. But I think so we have 20 minutes left to do this, and I think what I want to do actually first, to make sure we actually finish this and do it right, I'm actually going to jump and show you the theoretical math first, and then come back and do the lab. And so if we need to, we'll do the lab next time. Before we start any of this, the point is that we're going to simplify into a 3x3 space. So there are ages 0 to 19, or young folks. And you might actually, so you might ask yourself, what is going to be the fertility rate among Gesundheit, among those aged 0 to 19? So, and in the simulation, it's going to be like 0.6, I think, or something. And that's pretty high. So we're describing a society that is not like the contemporary United States, where there certainly are teenage births. That's the MTV show, right? The Teen Mom, Has anybody seen Teen Mom, by the way? Yeah, you guys have? So right, there's a character with my name on Teen Mom, right? And so if you Google Ryan Edwards, you'll find the Teen Mom guy. He has a different middle name, though. It's like Ryan C. Edwards, I think. Okay. So there are going to be teen moms in the data when we run this little forecast, this little model. But a lot of the fertility, of course, you would think normally comes from these ages, which is true in the modern United States. And then this age is going to be the folks, and I'm pretty sure they are zeroed out with fertility. And of course, that too is not realistic either. So what are the good ones there? Like Janet Jackson was like 50, I think, when she gave birth, right? I think J-Lo was like 40, I think. I don't think she was much beyond 40. But, motherhood past age 40 definitely is real. It is also true that, biologically speaking, it gets harder, especially for women after age 40. It also gets harder for men with age, and more risky because of the increased risk of mutation, it turns out, in the male contribution. But it's certainly not true about, male fertility usually stays decently high through this period, especially if you have pharmaceuticals. Female fertility in the modern United States is also decently high even in this period if you have pharmaceuticals. But I think in the forecast in the lab, we're going to assume it's actually 0. So you're dead if you reach age 60, and that's silly. Of course, there are all kinds of people who are over age 60 around, including Emeritus Professor Ron Lee. So maybe dead just means out of the model. You could think of it that way. And then each time a step of a matrix multiplication gives us 20 years of time. And so we recover annual rates in the lab by dividing the log of the ratio, let's say, by 20. And so that's a little confusing here. It's because the age groups are 20 years apart. So this is going to be one distinct group, and here's one distinct group. And you notice that if you add 20 years of age to each of these, then you get the next one up. So 0 plus 20 is equal to 20. 19 plus 20 is equal to 39, and so on. Okay. Where are we headed? Let me now show you the symbolic math behind this, and then I think we probably will end up doing the lab next time, given where we are. Okay. So here's where we're headed. The clever thing about this derivation is that you can write down something that's parsimonious using a few steps of logic here. So it counts today's people who are aged X, which is what we're looking at here. It's the age X people at time T. They are the surviving babies who were T minus X, indexed by that. So they were born X years in the past. So T is where we are today. They were born X years in the past, and then here is our survivorship probability, which again was that ski slope thing, right? So that's mortality. The survivorship probability is mortality, and it operates on these folks. So it's the provided that this is not changing over time. That's the other thing, right? There's no T. So this is true, turns out. And if births have been growing exponentially at rate n, so we're going to assume for simplicity that we'll have these cases where there's either positive growth or zero growth or negative growth, and that all is tied to this parameter little n. Then these births from X years ago are going to be deflated with this e to the minus nx. So it's the current level of births reduced by this factor that's equal to e to the minus nx. So it's the rate n over these X years of age. And so that then gives us a formula for the size of this population age group as a function of the current births, this thing, which is constant in n and whatever x happens to be, and also the constant mortality schedule Lx. Okay, so where next? Well, so this is what we derived. Now let's look at the share in this population age group nxt by dividing it then by nt, the capital nt, sorry. The uppercase nt without an x is just the total population. And so that's going to be our age structure defined as Greek letter nu of x and t. And you divide both sides of this thing by n, and notice that bt over nt is the crude birth rate. Okay, and if those are all constant, so the crude birth rate then is kind of it's crude, it's a rough measure of fertility. So assuming that thing basically is constant is sort of a reasonable starting place, and it then reveals this very useful relationship. Okay, so we've got the crude birth rate times this factor times survivorship, and that gives us the proportion of the population within a particular age range. So it's nu of x and t. So here then is our very confusing, I'll break it down for you in a second, picture of how these different pieces tell us about this, which is the schedule of the age structure with only one sex. So there's just women or men and women combined or whatever it is. And the way we're reading this is that as age rises, so this is basically half the population age pyramid, the orange line will give you a side of the thing that looks very much like a pyramid. The blue one, of course, gives you something that looks like half of a football. It's very, very much not at all a pyramid. And the black one is sort of in between. It's the product of this thing, the survivorship schedule, which, so recall where this thing comes from. So let me just show you that again, right? It was all the way back here, so we are on slide 35. And for US data, this is what we've got. Here's our survivorship curve. You can put it on its side and do that kind of thing. And so we're looking at this part of the survivorship curve here on slide 35. the middle thing is a little weird. This is what you get if you plot this function. So suppose you got some birth rate and you multiply it by e to the minus nx, and then you think about different n's, and oh my goodness, this is the gray one, which is almost invisible, isn't it? This is a flat line, so notice that if n is equal to 0, it's just e to the 0, which is just 1. So it's just a constant number starting here at 1 all the way up here, and I should really fix that. You can see it in the PDF, but unfortunately you cannot see it, I don't think, unless you really give yourself eye strain here. And the product of these three things then, I'm sorry, the last case is, so suppose you've got negative growth. Well, that means that, that n is actually a negative number, so this then e to the minus nx becomes e to the some positive number times x, and so it's rising over time, or age rather, up through here. And so this blue line then pushes the product of this thing up into a range kind of like this, where these are not themselves to scale. So let's break them down a little bit. So here's what you see if you've got just the orange ones. Your LX schedule here, you've got your minus NX, where the N is some positive growth rate. And so the product of these things then gives you this H structure that's very much like a pyramid, except it's sort of bowed out here in the middle. So that's the classic story of a developing country with fairly high fertility. The crude birth rate is high, and that then will give you this kind of picture of the H structure. A very classic pyramid shape, except maybe it's a little bit more sort of bowed out here if you believe the math. Okay, and here's going to be our problem again. I'm so sorry. It's the ghost line. It's that thing that's just perfectly vertical. So, you know, if this is just equal to 1, it just recreates exactly the survivorship curve, and that's the H structure if you've got a population that's not growing at n equals 0. And then finally, this is probably the best one to break it out with here. And this is, you know, not to scale with the others. If this thing starts exploding, well, survivorship pulls it down to Earth at some point, but it bows out the middle quite a bit as this is larger. And it has to come back to Earth, and it's got some level down here. But it increases this, and so you would see this thing, and of course, that's an old friend, right? So here we are on slide 38. Let's go all the way back to our friend Japan, right? We saw it way back here. So a big reduction in population growth rates because of very low fertility, and we're seeing that kind of thing. But if the vital rates were the same, the answer to this riddle, the father's riddle, if the population has very low fertility, won't it just keep getting older and older and older? The answer is no. In the formal math, it will actually reach a stable population age structure that would look like this, provided that you've got some kind of stable but low growth rate, because the birth rate, whatever it is quite low. So this is the case where the intrinsic growth rate is very low. It's because births are low, but we're not thinking about measuring, you know, that through the crude birth rate. The key thing is whether or not this is really changing in Japan. And of course, in reality, that is. The survivorship schedule actually is becoming even more ski slopety. It's becoming, you know, even further pushed out. People are living longer and longer, which of course is a very good thing, but it means that the age structure in Japan probably will technically get older and older. If it were somehow stuck, it wouldn't. You'd see this thing just forever. Okay. So 3 different cases now with both sexes shown. So we're taking each one of these pieces and just putting it in a mirror, right? So the case 1 then is positive growth given some kind of stable survivorship. 0 growth, you see something that looks somewhat like a pyramid, but a little bit less so like this, and then negative growth. So that's, you want to think of that being Japan, basically. And which is best? Well, there are different reasons why different ones of these are good, but you know, because maybe this one, right? This is like mama bear, papa bear, and wait, I'm sorry, mama bear, papa bear, and baby bear. Right? Baby bear is probably the best. It's in the middle. I don't know which one's best. Here you've got this big dependency burden derived from kids, right? There are a lot of children here in the population. Here you've got a lot of seniors in the population. And probably both of those are kind of, you know, either too hot or too cold, and the middle one is probably just right, I guess. Maybe there's something deeper to it than that. Okay. So in the 10 minutes we've got left, why don't we give this a shot? Let's look at the lab. So what we're going to do in the lab is actually use some matrices to look at this. So I've got my RStudio locally set up. Maybe I'll just do that. Okay. All right. So in the in-class lab, what we're doing is projecting a population with these 3 different age groups using matrix multiplication. Can everybody see this okay? Is that fairly visible? Okay. So we've got, okay, the transitions between these different age groups, and I think what was useful to me is to think about putting them into a spreadsheet. So let me try to make these a little bit bigger. Okay, so here's our index of time up here. So here's the current year, here's 20 years later, 40 years later, and 60 years later. And suppose we started with these numbers of people. So 20 years later, this group where the cursor is going to be this group, but then decremented by whatever the survivorship is, right? So if the survivorship then is 90%, where you've got 90% of the folks in that age group of 0 to 19 surviving into 20 to 39, you'd see this. And so let me think if I maybe want to do something like that. So 50 folks then end up being 45, and already we're at a different population count than 20 years later. And then this one is similar. These 30 folks then are going to age into this cell at this rate. So 70% then will survive into this higher age range. And then the tough one is, well, what is the number of people age 0 to 19 here? So our assumptions are going to be that these are, and I think the right term here, and please correct me if I'm wrong about this. I think it's the net reproduction ratio. So it's the net people per person then who are show up again. So it's right. It's the number that we've got. There's no more mortality that's going to factor in here. We'll think about that, but I think that's the technical term. It's not the total fertility rate, I think. So suppose that. How many of these 0 to 19-year-olds show up? Well, it's going to be 0.6, and this is a very high rate of reproduction then for whoever used to be 0 to 19. So those folks are having children, plus a 0.8 rate of these guys, the 30-year-olds. And so that's what that happens to be. And so if I'm smart, I should probably try to put these dollar signs around that. Okay. And then here, I suppose I should have put in another row for the sum. Okay. So net population growth with these rates. And this is just meant to help you kind of visualize what's happening, and it'll be easier once we do the matrix notation, provided I haven't confused us all. And of course, the magic of spreadsheets is if I coded this right, hopefully it's going to give us the same kind of dynamic, just copying it over, and obviously something was wrong. Okay, so what did I do wrong here? Let's see. Oh, I put the dollar signs on the wrong cells, didn't I? Yeah, that can happen. All right, so it's B14 that gets fixed, not that one. That one I got right. That one I got right. Let's try that again. Oh, I see. I didn't do anything right with this. Let's see. There we go. Okay. Well, we'll see if I coded that correctly or not. Okay, so each period, these folks march on down to be these folks, right? That's the aging. You're 0 to 19 in the first period. 20 years later, you're 20 to 39. And that's kind of what ought to happen. So now let's click back over into RStudio. And here's if you like thinking about, this is the setup basically of what's called a Leslie matrix, which is counting the groups coming in versus the groups going out into the next population vector. Okay. And here's some nifty matrix notation. All right. So one of the neat things about R Markdown, and if you've taken data science, you might be using like Jupyter Notebook or something, but all this is the math type, which you of course have seen in the other labs. Powerful, cool stuff that just then becomes this elegant math, which is similar to what we saw on the slides. Okay. So let's take a particular example of a projection matrix, and here, hopefully I've copied everything down. So the 0.6 then is this total fertility rate, or I should say the NRR, right, associated with the first group. So let's go back to our matrix notation back here. So it's this guy. It's A11 times P1, which is going to give us the new births associated with the parents who had been 0 to 19. And then here is the births associated with the people in age group 2. Okay, and then our starting population vector, this guy, 50, 30, 20, which I think is what I had written down over here. Okay. So now let's do this in R. First by hand, then we can check what is the population after one projection step, and hopefully if I coded it right, it should be this, 120. And then you might look at the ratio of total population size at the first step, which is this to this, and that's pretty easy to eyeball, provided I did it right. It's 20% bigger, or 120% the size. Okay, so let's do this. So here's our R code that creates a matrix out of this, I guess probably column vector that we're passing it and telling it to give us 3 columns. So here I run that, and here's our, I see what we're printing out is A times P0, which is the first step there, 54, 45, and 21. That looks like I did it right. So that's the population at the first step. So what we have done, let's see if I can do this symbolic math again back here again. We've taken the first population vector here, and we've applied this growth matrix. I probably should have written that out. It's the one that's got 0.6 right here, and 0.8 and 0, and it's got a 0.9, that's a survivorship, and a 0 and a 0, and a 0 and a 0.7, I think, right there for that. And so now we've plopped that out. Here we'll run this bit of code, which looks at the ratios of population sizes, and there's our 1.2. And so this is probably the trickiest part, and it, I think, shows up fairly frequently in the labs. Suppose you wanted to annualize the growth rate. Here's a 20, and the reason is we've got age groups that differ by 20 years between them. So we want the annual growth rate to reflect this issue. And so the log of the ratio divided by the number 20 then gives us a number that's just about 1% growth. If you eyeball this, of course, this is, you could, right, so 20% increase over 20 years is in the neighborhood of 1% exponential growth, and that's what we see here. So we're out of time for today. We'll finish this up next time and then move on to Social Security.